Good morning and welcome to today's lecture. Today we shall discuss binary systems. Let me remind you that we have already discussed the motion of a test particle in the gravitational field of another object whose mass is much more than that of the test particle. So, this is the problem that we have discussed, and the test particle m is assumed to be much smaller than the have a mass that is much smaller than the mass whose gravitational field we are interested in. And essentially we can ignore the gravitational effect of the test particle on this object. Under this assumption, the equation of motion of the test particle, which we have already discussed, let me remind you again that the equation of motion is r double dot, the acceleration of the test particle, is equal to minus g m, where m is the mass of the object that is exerting the gravitational force, minus g m by r square, and I write it as the vector r by r cube. So, this is the 1 by r square law. So, this is the motion of a test particle around a very massive gravitating object. Now, today we shall be discussing a different system. Here we have two masses m1 and m2. And these masses may be comparable. So, this is the vector r1 with reference to some arbitrary origin. This is the vector r2 corresponding to the two different masses, and these masses may be comparable. So, this is the system that we refer to as a binary. For example, we may have two stars in a bound orbit. Okay. So, this is the system that we are interested in, and let me write down the equation of motion for this system. So, this is the vector r, it points from r1 to r2. So, r is equal to r2 minus r1, and r is the relative displacement between the two particles. Now, we all know how to write down the equation of motion of these two particles. So, let me do that. So, for the particle m1, we have m1 into r1, the acceleration of the first particle. So, let me put a line here to differentiate between these two. This is, so the rate of change of momentum of the first particle is equal to minus g m1 m2. So, the gravitational force is proportional to the product of the two masses and the inversely proportional to the square of this distance, and it is pointed towards the second mass. So, there will be a plus sign here, and it will be r by r cube. Similarly, I can write down the equation of motion of the second particle. So, this will be m1, and equation of motion of the second particle will be m2 r2 double dot is equal to, now this force will be opposed to r. So, I have to put a minus sign, g m1 m2, and the same thing r by r cube. Now, the question is, how do we solve the equation of motion of these two particles? You can see that they are coupled. So, the motion of this particle depends on this, the coordinate of this particle, and the motion of this particle depends on the coordinates of this particle. We have to simultaneously solve both of these equations. So, to do that, it is convenient to change the coordinates instead of using r1 and r2, which refer to the two individual particles. It is convenient to use different coordinates, and these different coordinates are the relative displacement between the two particles, which we have already introduced, and the position of the center of mass r. Center of mass is defined as m1 r1 plus the weighted average of the two vectors m1 r1 plus m2 r2 divided by m1 plus m2 that is the center of mass. So, instead of using r1 and r2, we shall now be using the relative displacement and the center of mass to describe the system. So, we had two vectors, we again have two vectors, and we can equivalently use these two instead of these two. So, in terms of these two vectors, what are the equations of motion? So, let us first work out the equation of motion for the center of mass. This can be worked out by just adding these two equations. If I add these two equations, what I get is r double dot is equal to 0. So, what we see is that the center of mass of the two particles moves like a free particle. There is no external force acting on the center of mass. So, the combined system, the system made of these two particles combined, can be thought of as the motion of the center of mass, and that moves like a free particle. So, if it is at rest to start with, it will remain at rest, and if it is in uniform motion, it will continue to move with whatever velocity it has. So, this is like a free particle. And for the subsequent discussion, we shall assume that we are in the frame of reference where the center of mass is at rest. So, this is the motion of the center of mass. The next thing that we have to work out is the equation of motion for the relative displacement r, and that can be worked out by dividing this equation by m1 and dividing this equation by m2 and then subtracting this equation from this equation. So, let me remind you again what you have to do. You have to divide this equation by m1, divide this equation by m2, and then you just look at the difference of these two equations. That will give you the equation of motion for r2 minus r1. And what do you get? What you get is that r double dot is equal to minus g m1 plus m2 r by r cube. That is what you get. So, what you see is that the difference vector, the relative displacement between the two particles, that is governed by this equation, which is exactly the same equation of a test particle in motion around a very massive object of mass m. So, the separation vector between the two particles behaves just like the motion of a test particle in the gravitational field of an object of mass m1 plus m2. And we have already discussed the motion of such an object. We have already discussed the motion of such an object, and we have seen that the orbits are ellipses, and we can interpret them in terms of the three Kepler's laws, the ellipses. So, we have already discussed this, and we shall not repeat the discussion once more. So, what we learn from this is that the two body problem, where you have two masses, comparable masses in gravitational motion in each other's gravitational field, can be reduced to a single mass moving around a single object moving around in a central potential, in a central force of a very massive object, where we can ignore this particular mass. So, the problems are equivalent, and we know that the solutions are ellipses and all of the Kepler's laws will hold. So, once you know how the relative displacement between these particles evolves as a function of time, you can easily work out what R1 and R2 will now do. And let me remind you again that we are going to work in the center of mass frame of reference, where we are at rest at the center of mass of these two systems. So, the center of mass is at the origin. So, this is 0. So, we have M1 R1 is equal to minus M2 R2, and we can put this in to this equation, and what we will get is that R2 is equal to M1 by M1 plus M2 into R. R1 is equal to minus M2 by M1 plus M2 into R. So, we see that R2 by R1, the ratio of the magnitude of the vector R2 by R1 is equal to M1 by M2. So, this is all consistent with this. Okay. And we have, let me remind you that we have seen that the vector R sweeps out an ellipse with semi major axis, let us say A, then R1 R2 will also sweep out an ellipse whose semi major axis is A2, which will be M1 by M1 plus M2 A, and R, the vector R will also sweep out an ellipse, and this will have A1 is equal to M1 by M1 plus M2 into A. So, let me now show you an example of what the orbit looks like. So, this picture on the computer screen shows you the motion of two objects which are moving in each other's gravitational field, and the object, the ratio of the masses M1 is to M2. So, we are considering a particular situation where M1 is to M2 is equal to 1 is to 0.6. So, you would expect the semi major axis of the second particle, of the less massive particle, to be larger, the semi major axis of the more massive particle to be smaller. So, the more massive particle is going to have a smaller orbit, the less massive object is going to have a larger orbit, such that the center of mass remains fixed. So, let us look at the picture again. Here the center of mass is located at this point. The two objects are going to be located at two different sides of the center of mass. So, the relative displacement between these two objects is always going to pass through the center of mass. This sweeps out an ellipse, this also sweeps out an ellipse, this is more massive than this. So, the radius of this, the semi major axis of this ellipse is smaller, the semi major axis of this ellipse is larger. So, when this object is here, when the second object is here, the first object is here, then the first object moves in this direction, the second M2 moves in this direction, and they have exactly the same time period, and the line joining them always passes through the center of mass. These distances are in the ratio 1:0.6. The semi major axes are also in the ratio 1:0.6. So, this is in general what the orbits look like for binary systems. Now, let me now tell you what we are going to discuss in today's lecture. Today, we are going to consider a system where we have two stars in binary orbit. So, two stars which are moving in each other's gravitational field. So, we have learned about our solar system, and in our solar system there is only a single star, the Sun, and we have all the planets going around, revolving around the Sun. So, our system is obviously not a binary system. So, the question arises, why are we so interested in binary stellar systems where you have two stars? Well, let me give you some motivation for this. Well, it is an observed fact that half to two-thirds of all the stars are in binary systems. So, our solar system, which has only a single star, is more of an exception than a rule. Roughly half to two-thirds of all the stars are found in binary systems. Now, both of the stars, as we have seen, rotate around the common center of mass. That is what we just saw. So, in all of these systems where you have two stars, they both rotate around a common center of mass in orbits that look something like this. And the center of mass is also referred to as the barycenter. The periods could be from days to years for normal stars. So, normal stars are stars that look like our Sun, maybe somewhat larger, somewhat smaller. They all burn hydrogen. This is something that we shall discuss in much more detail later. Now, the periods could be much less, could be hours and less, if one of the stars is a compact star like a white dwarf or a neutron star. We have seen that the period depends on the orbital of the semi major axis of the orbit, and the smaller the semi major axis, the smaller the period. So, if you want a small period, the semi major axis of the orbit also has to be small, and the stars also have to be small if they have to orbit in a very close in a small elliptical orbit. So, if you have compact stars, if one of the stars in the system is a compact star, or if both of them are compact stars like neutron stars or white dwarfs, or one of them could be a black hole, then you have periods which could be hours or even less. Now, binary stellar systems are some of the most interesting things that one could study. They are actually laboratories, astrophysical laboratories. Why? Well, observations of the orbits can be used to determine parameters of the stars. If you have an isolated star, for example, it is extremely difficult, if not impossible, to determine the mass of the star. For example, the mass of the Sun can be determined from the period of the Earth's orbit using Kepler's laws. We know that the period and the orbital, the semi major axis are related through the mass. So, if you can measure the period and the semi major axis, you can determine the mass. So, individual stars, it is very difficult to determine the mass of the star, but if you have a binary system, you can determine various parameters about the stars like the mass, and this is done in optical and in X-ray. So, they are very useful laboratories where you can determine different parameters from the period and the line of sight velocity. You can determine the mass of the stars. The second thing that you can learn from binary system is the fact that you have a large fraction of stars in binaries, and individual stars are rather rare. This is an indication that stars are formed in groups through the gravitational collapse of a gaseous cloud. So, when in the interstellar medium you have these gas clouds, and when such a cloud collapses, you do not form a single star, but you form several stars simultaneously. And the fact that you have binary systems in excess of individual stars gives us a handle on the star formation process. You have different kinds of binary systems where both of the stars are normal stars. You could also have binary systems where one of the star is a white dwarf or maybe a neutron star, and the fact that you have this variety of binary systems provides tests of models of stellar evolution. And very interestingly, when you have two stars in close proximity orbiting one another, it is possible that there could be mass transfer from one star to another. This is what is referred to as accretion. And an isolated star would evolve in a particular way, it would lead its life in a particular way, whereas if a star were to receive material from outside, it would completely change its evolution. So, very interesting physical phenomena take place in binary systems, and which affects the evolution of the stars. And accretion may also dramatically change the nature of the stars. For example, there are binary stars called binary pulsars, which are formed. Some of these are formed during accretion in binary systems, very high millisecond binary pulsars. So, a variety of phenomena take place in binary systems, and one can study. So, interaction between different kinds of stars, a variety of such phenomena can be studied using binary stellar systems. Now, there are typically three different types of binary stellar systems. So, we have the visual binary, the eclipsing binary, and the spectroscopic binary. These are the three main types of binary stellar systems. And we should note that these types are not mutually exclusive. So, there could be a stellar system, binary stellar system, which is both a visual as well as an eclipsing binary, or a visual and a spectroscopic binary. There is another type called an astrometric binary, where you only see one of the stars on the sky, and you know that it is a binary. You infer the fact that it is a binary, it is a part of a binary system, from the fact that the star seems to wobble because of its motion around the common center of mass. You do not see the partner. Such stars where you only see one of them and it wobbles is called an astrometric binary. So, let me now go in some detail, not very much, in some detail tell you about these three different types of binary systems: the visual binary, the eclipsing binary, and the spectroscopic binary. Before that, we need to introduce certain nomenclature. So, we have the inclination of the binary system, the inclination angle. So, this picture shows you a binary orbit, and this is the plane of the orbit, and the observer is located in this direction. So, the observer is looking at the orbit at an angle called the inclination angle, which is the angle between the direction at which the observer is looking at this, the direction to the observer, and the normal to the plane of the orbit. So, this is the inclination angle. If the orbit is, if you have an inclination angle of 0, it essentially means that the orbit is face on, you are seeing the orbit face on. So, it is like this. The binary system is you are seeing it like this, the star is going around like this and you are seeing it face on. Whereas, if the inclination angle is 90, you are seeing the orbit edge on like this. The plane of the orbit is like this, the star is going around like this in this plane and you are seeing it edge on. That corresponds to 90 degrees. So, let me repeat, an inclination angle of 0, the orbit is being viewed face on. Inclination angle of 90, the orbit is being viewed edge on, and other angles lie in between these two extreme cases. So, the first type is the visual binary, and this picture shows you a particular case of a visual binary. So, this picture shows you the star Sirius A, and this star is the brightest star in the sky, and it is also the nearest star that is visible to the naked eye. So, this is Sirius A, the brightest star in the sky. What is interesting from our point of view is that there is another star which you would not notice if you were to look at this Sirius A, and this star is called Sirius B, and Sirius B is a white dwarf. It is a very small star, and the arrow here shows you the location of the white dwarf, it is over here. So, the white dwarf and the Sirius A, so Sirius A and Sirius B form a binary system, and this binary system has a period of around 50 years. And a visual binary is a system where you can see both the stars in a photographic plate or a picture of the sky. So, a visual binary refers to a binary system where both the stars are visible in a photographic plate or an image of the sky. And if you wait for 50 years and if the so you can then see the orbit, you can then see the two stars moving around on the sky, and from where you can infer certain properties of the orbit depending on the inclination angle, which in general is not known, but you can make out certain properties of the orbit for a visual binary. You will see the two stars moving around over the course of time. So, this is the first type of binary, the visual binary. And so, let me repeat again, both stars are seen in images of the sky, and in some cases it is possible to map the motion in the sky and determine important parameters like the mass. Example is Alpha Centauri. Let me now move on to the next kind of binary system, which is an eclipsing binary. So, in an eclipsing binary, you typically do not see the two stars as distinctly cannot make out the two stars in an image of the sky. So, the question is, how do you know that you have a binary system? Well, you know that you have a binary system because of the fact that one star goes behind the other, creating an eclipse. So, this is a situation where one star eclipses the other, and question is, what do you require for an eclipsing binary? Well, for an eclipsing binary, in general the two stars should be sufficiently close. So, if you have two very distant stars, it is highly unlikely that one of them will block the other. Further, one of them should be large enough to block the other star, and the inclination angle should be close to 90, or else it is unlikely that one of these stars is going to block the other. For a face on orbit, it is not going to happen that one of the stars is going to block the other. So, you require the inclination angle to be close to 90. Now, the first two conditions are satisfied if the ratio of the radius of the star and the separation between the two stars is approximately 1. If this condition is satisfied, then the inclination angle also need not be very close to 90, and you will have an eclipse for a large variety, for a large range, relatively large range of inclination angles. So, the situation is that one of the size of the star should be comparable to the separation between the two stars. This is the situation. If you have such a situation, then for a large range of viewing angles, one of these you are going to have an eclipse. Okay, so such a situation is very favorable. If this is R and this is S, the separation, such a situation is extremely favorable for an eclipsing orbit. So, when one of these stars goes behind the other, okay, so we are considering a situation where we cannot distinguish the fact that there are two stars on the sky. In an image of the sky, we cannot make out the two stars, but there will be a reduction of light when one of the stars goes behind the other, and this is how we can make out that there is an eclipsing binary. So, let us briefly now discuss what kind of a reduction of light you expect and its visible consequences. So, let us consider a situation like this, a hypothetical situation like this, where you have two stars, one of them is rather big and the other one is smaller, and they are going around in a circular orbit, and the observer is located over here. So, when this star is behind, then the small star, let us call this A and this B, when B is behind A, it is completely eclipsed, and then it comes around and you can see both the stars, and then B comes in front and it obscures out a part of A, and then again it moves out. So, question is, what will the total light that comes from this system look like? That is the question. This is what is called the light curve. So, let us try to make an estimate of what the light curve from such a system will look like, and we will assume that the smaller star is cooler than the larger star. So, we will assume that the larger star is hotter and the smaller star is cooler. So, and we know that the radiation that you receive from any star per unit area of a star is proportional to sigma T to the power 4. The flux of radiation from per unit area of a star is proportional to sigma T to the power 4. So, the radiation per unit area from this star, from the bigger star, is more than the radiation per unit area from the smaller star. So, let us now try to schematically draw the light curve for such a star. This is the total radiation, flux of radiation coming from the star. So, let us start with a situation where both the stars are visible, and in such a situation the light that you will receive is the combination of both A and B, and then let us consider the situation where B is completely obscured by A. So, if B is completely obscured by A, the light from B, contribution from B is blocked out, and for a certain period, and this is what you get. Next, again you can see both of them, and then B comes in front. Question is, what happens when B comes in front? When B comes in front, it blocks out a certain part of the hotter star, and that gets replaced by an equivalent part which is cooler. So, the radiation that you receive in this situation is actually going to be lower than the radiation that you receive when B is completely blocked out. So, the light curve from the two stars will look like this, and this corresponds to the situation where B is obscured by the brighter star, hotter star, and this is the situation where the cooler star comes in front of the hotter star, which is larger. So, this is what the typical light curve is going to look like, and if you can measure the different intervals, time intervals, you can infer very useful information about the different stars in the orbit. So, this is the eclipsing binary, and an example is Algol, and one of the stars in this eclipsing binary is a main sequence star. Main sequence star is a normal star like ours which burns hydrogen, and another star is a subgiant. It has a period of 2.9 days. Well, the period has to be small, will typically be small in an eclipsing binary, because we have seen that the distance between the two stars should be comparable to the radius of the star. If you want the probability for an eclipsing binary goes up if you have this situation. So, typically the eclipsing binaries will have a very small orbit of the semi major axis of the orbit will be small. So, the period is also going to be small, and in this case we have a period of 2.9 days, and the orbit is the separation between the two stars is just 14 times the radius of the sun. So, it is an extremely tight orbit, just 14 times the radius of our sun, and the two stars in this binary system subtend 2 millisecond of arc in angle. So, in the usual traditional imaging, you will not be able to make out that there are two stars in the sky, but if you use high resolution imaging like interferometry or adaptive optics, you can make out this separation 2 milliarc second separation in the sky, and you can distinguish and make out the fact that there are two stars. So, finally, let me come to the third type of binary system, which is a common. So, these are spectroscopic binaries. Again, these are systems where you need not make out that there are two stars. So, looking at an image, you would think that there is just a single star in the sky. Then the question is, how do you make out that you have a binary system? Well, here we shall answer that question as we go along. So, what is a spectroscopic binary? Here again we have two stars which are very close, typically less than 1 astronomical unit, and we make out that we have a spectroscopic binary from the Doppler shift of spectral lines. So, the basic idea is that you have to be able to identify spectral lines coming from the two distinct stars, and as the stars move around you will have Doppler shift, and since the two stars have different motions, you will have different Doppler shifts for the two different lines, and then from that you can make out that you have a binary system. For appreciable Doppler shifts, you need the velocities to be high, and for the velocities to be high, the orbits that have to be, the semi major axis of the orbit has to be small, which is why you require them to be in the two stars to be very close. So, for a circular orbit, we know that v square is proportional to 1 by r, right. So, you would like the velocity to be large. So, the radius, the separation between the orbit between the two stars has to be small. So, the Doppler shifts of the two stars should be discernible. Further, the stars should be bright so that the spectral lines can be measured with a high signal to noise ratio. After all, you have to determine the Doppler shift of the spectral lines, and for this you require very high signal to noise ratio spectral lines from the stars. So, the stars have to be bright. Now, very often spectroscopic binaries are also eclipsing. because the two stars are very close together. So, very often they are also eclipsing. So, this is what is a spectroscopic binary. They are typically stars which are very close together, very bright, so that you can make out spectral lines. So, let me try to explain to you what will happen if you have a spectroscopic binary. So, this picture shows you a binary system of two stars in circular orbit. Circular orbit has been particularly chosen to keep the analysis simple. So, you have these two stars going around in circular orbit around the common center of mass over here, and the black object is less massive, the blue object is more massive, and they are both doing circular orbits, and we start from the position A, where one of the objects is here and the other object is over here, and the orbit is circular. So, and the observer is located in this direction. So, in the position A, there is no velocity component of the motion along the line of sight, and it is the line of sight motion that causes component of the velocity that causes the Doppler effect. What is the Doppler effect? Let me remind you, the Doppler effect is a shift in the wavelength of a spectral line. So, there is a spectral line which is emitted at a wavelength lambda, and if the source is moving with the velocity v, then an observer will see a shift in wavelength, and the shift in the wavelength delta lambda is such that delta lambda by lambda is equal to v by c. So, it is the fractional shift in the wavelength is proportional to the speed with which the object is moving, and it is only the line of sight component of the speed. So, it is only the component in this direction, and if the source is moving away from the observer, then the velocity is positive and there is a positive shift in the wavelength increases. This is called a redshift. This is called a redshift. So, delta lambda greater than 0 is called a redshift. This happens if the source is moving away from the observer. If delta lambda is less than 0, you have a blue shift. This happens when the source is moving towards the observer. So, in this position A, the source has no velocity component relative to the observer's line of sight. So, the spectral line is observed where you would expect it at the wavelength lambda. There is no shift in the wavelength. Now, after some time, the star A, the star over here has moved to position B. Similarly, this has moved to this position B, and we now have a line of sight component of the velocity. So, the velocity is tangential, we have a line of sight component of the velocity, and this object is moving towards the observer. So, we have a blue shift. This object is moving away from the observer. So, we have a red shift. So, the wavelength of this object in position B has shifted, it has become less, whereas the wavelength emitted from here the object here is moving away from the observer. So, the wavelength has increased. Now, when it moves from position B to position C, the line of sight component of the velocity has increased further. It is now completely along the line of sight. So, the shift in the wavelength has also gone up. There is a larger shift in the wavelength, and then in position D, again the line of sight component of velocity has gone down. So, it has decreased, and then it will move to this position where there is going to be no shift at all, and then it will repeat. So, this will now so the wavelength, the shift in the wavelength is going to go up and down like this. Similarly, this wavelength is going to go up and down like this. And if I plot the wavelength, the wavelength can be used to infer the line of sight component of the velocity. The shift in the wavelength can be used to infer the line of sight component of the velocity, and this is what the line of sight component of the velocity looks like. So, in position A there is no line of sight component of the velocity, in position B it has gone up, position C it has gone up further for this object and then it reduces and it becomes negative in this half and again positive. For the second object, it starts off with 0 and then you have a negative line of sight component, it becomes negative, it is moving away from the observer and then it again goes down like this. So, you will see that there are two spectral lines shift, and from there you can infer for a spectroscopic binary you have, if you can determine spectroscopic lines from the two different objects, these two spectroscopic lines will shift, the shifts will be pi out of phase because the motions of these two objects are exactly pi out of phase, and they will, in this particular case you will have exactly sinusoidal behavior with time. The two sinusoidal curves are exactly pi out of phase. So, this is these are characteristic features of spectroscopic binaries. In a spectroscopic binary, you have two velocity curves. If you can identify two spectral lines from the two different objects, then you will find that they have two different velocity curves which are exactly pi out of phase. The velocities of the two objects, the radii of the two objects are inversely proportional to the masses, and the velocity V1 is proportional to, for a circular orbit, omega into A1, V2 is equal to omega into A2. Omega is the angular frequency which is common for both of them, and A1 and A2 are inversely proportional to the masses. So, the velocities also are inversely proportional to the masses, and this is true even for elliptic orbits. So, the amplitude depends inversely on the masses. This is another characteristic feature. So, here the amplitude of the less massive object is more and the amplitude of the more massive object is less. So, the ratio of the amplitudes of the velocities tells you the ratio of the masses. And an example is phi Cygni. For phi Cygni, the velocity curve is asymmetric. So, what we have considered over here is a circular orbit. In general, the circular orbit will not be, even if you have circular orbit, it will not be exactly in the plane exactly edge on, it will not be viewed exactly edge on, there will be an inclination angle, effect of an inclination angle, and typically you will not have circular orbits, you may even have elliptic orbits, and for elliptic orbits you will not have exact sinusoidal curves like this, you will have asymmetric curves, which is the situation for phi Cygni. And there are situations where only one of the binary elements is seen in the spectroscopic line, and these are called single line spectroscopic binary. So, let me now briefly recapitulate what we have learnt today. Today we have been discussing binary systems where you have two objects in a binary orbit in an orbit in each other's gravitational field, and we saw that this can be reduced to exactly the problem that we had discussed earlier, where you have a test particle moving in the mass of in the gravitational field of a much larger mass m. So, the two body problem of a binary system can be reduced to a one body problem if we go to the center of mass frame of reference, and the one body and the displacement, relative displacement between these two particles behaves in exactly the same way as a single particle, test particle in the gravitational field of a much more massive object. That is the first thing. So, each of the displacement vector between these two particles traces out ellipses, an ellipse follows Kepler's laws, and each of the particle also traces out ellipses and follows Kepler's laws. The radii are inversely, the ratio of the radii is inversely proportional to the masses. Then, having told you this, I gave some motivation why we are interested in binary systems. A large fraction of the stars are found in binary systems, and they are also very useful laboratories for studying a variety of things, including they are possibly the only situation where you can determine the mass of stars, and they also let us study the interaction accretion between stars. And finally, I told you that there were three kinds of binary stellar systems: the visual binary, eclipsing binary, and spectroscopic binary. These three types are not mutually exclusive. So, you could have a binary system which is both a visual and a spectroscopic binary, for example. And then I briefly discussed each different type of binary system. So, let me bring our today's discussion of binary systems to an end over here. In the next lecture, I shall resume our discussion of binary systems. The equation of motion of the second particle will be m2 r2 double dot is equal to, now this force will be opposed to r. So, I have to put a minus sign g m1 m2 and the same thing r by r cube. Now, the question is, how do we solve the equation of motion of these two particles? You can see that they are coupled. So, the motion of this particle depends on this, the coordinate of this particle, and the motion of this particle depends on the coordinates of this particle. We have to simultaneously solve both of these equations. So, to do that, it is convenient to change the coordinates. Instead of using r1 and r2, which refer to the two individual particles, it is convenient to use different coordinates, and these different coordinates are the relative displacement between the two particles, which we have already introduced, and the position of the center of mass r. Center of mass is defined as m1 r1 plus the weighted average of the two vectors m1 r1 plus m2 r2 divided by m1 plus m2 that is the center of mass. So, instead of using r1 and r2, we shall now be using the relative displacement and the center of mass to describe the system. So, we had two vectors, we again have two vectors, and we can equivalently use these two instead of these two. So, in terms of these two vectors, what are the equations of motion? So, let us first work out the equation of motion for the center of mass. This can be worked out by just adding these two equations. If I add these two equations, what I get is r double dot is equal to 0. So, what we see is that the center of mass of the two particles moves like a free particle. There is no external force acting on the center of mass. So, the combined system, the system made of these two particles combined, can be thought of as the motion of the center of mass, and that moves like a free particle. So, if it is at rest to start with, it will remain at rest, and if it is in uniform motion, it will continue to move with whatever velocity it has. So, this is like a free r double dot, the acceleration of the test particle is equal to minus g m, where m is the mass of the object that is exerting the gravitational force, minus g m by r square, and I write it as the vector r by r cube. So, this is the 1 by r square law. So, this is the motion of a test particle around a very massive gravitating object. Now, today we shall be discussing a different system. Here we have two masses m1 and m2. And these masses may be comparable. So, this is the vector r1 with reference to some arbitrary origin. This is the vector r2 corresponding to the two different masses, and these masses may be comparable. So, this is the system that we refer to as a binary. For example, we may have two stars in a bound orbit. Okay. So, this is the system that we are interested in, and let me write down the equation of motion for this system. So, this is the vector r, it points from r1 to r2. So, r is equal to r2 minus r1, and r is the relative displacement between the two particles. Now, we all know how to write down the equation of motion of these two particles. So, let me do that. So, for the particle m1, we have m1 into r1, the acceleration of the first particle. So, let me put a line here to differentiate between these two. This is, so the rate of change of momentum of the first particle is equal to minus g m1 m2. So, the gravitational force is proportional to the product of the two masses and the inversely proportional to the square of this distance, and it is pointed towards the second mass. So, there will be a plus sign here, and it will be r by r cube. Similarly, I can write down the equation of motion of the second particle. So, this will be m1, and good morning and welcome to today's lecture. Today we shall discuss binary systems. Let me remind you that we have already discussed the motion of a test particle in the gravitational field of another object whose mass is much more than that of the test particle. So, this is the problem that we have discussed, and the test particle m is assumed to be much smaller than the have a mass that is much smaller than the mass whose gravitational field we are interested in. And essentially we can ignore the gravitational effect of the test particle on this object. Under this assumption, the equation of motion of the test particle, which we have already discussed. Let me remind you again that the equation of motion is